first presentation is Oyarhossein, Mohammad Oyarhossein, who's a graduate student here in civil engineering. And he's going to give his talk on carbon dioxide and hydrogen storage in salt caverns, and it's the title of the slide that you see on the screen. Please, Mohammad.
Thank you very much, Professor Dusseault. Good afternoon. My name is Mohammad Oyarhossein. I'm a PhD student here at the University of Waterloo. Basically, I'm not within the member of the Compass A group, but I decided to think about geomechanical aspect of CO2 sequestration and hydrogen storage. I'm going to talk about why having salt caverns is important, why storing is important. Then I'm going to talk about what will be my objective of these things. We will go and review some kind of two case histories we have for CO2 and H2. Later that, I'm going to talk about what was my contribution for this course and for this topic, and then I will conclude my presentation. Well, salt cavern is really important. Like if you start reading paper, if you start going through journals, or if you just Google environmental or sustainable energy, people you'll see like thousands of papers and presentation and talks. Well, there are different ideas about that. Where some people believe that we can have like 100% renewable energy. Some people say, hey, you know what, we just started. Personally, I believe we are almost there. There are many rooms for studying more. There are many rooms for researching. So I would say we're almost there. We just need to concentrate and research and get there. For the presentation today, I decided to talk about CO2 sequestration and H2 storage. And I'm not going to talk about any kind of like grid things, whether they're good for grid or whether they're environmental or not. I just focus on geomechanical aspect of that because I'm a geomechanical engineer at the end of the day. So the objective is to understand the geomechanical aspect of storing H2 and CO2 in salt formation. But I'm focusing myself in salt. First site for CO2 sequestration proposal I found, it's called Lotsburg. It's basically close to Edmonton, if you can see my laser. It's northeast. It's closer to Edmonton rather than Calgary. And basically it is the place when we have other source of shale gas or oil sands. It's not very shallow, it's not very deep. It's something like 1,200 deep. And it's basically surrounded by two sandstone and shale formation. So it is Alberta, closer to Edmonton, and it's something like in between, not very deep, not very shallow. The proposal for making a well construction is having a 12¼ inches hole for 200 meters as a surface casing, and then cement that. We can have a 9-inch borehole going 3 meters above the layer of that formation. At that point, we can have some hydraulic fracturing tests for determining sigma-3 minimum stress. If you would like to think about free creep of that salt formation, we can have a pilot hole, can be 6¼ inches. And of course, we can dissolve that salt with 2 tubes or concentric string. The scenarios for filling that cavern were basically like this. The design was between 8 to 12 megapascal is the pressure, internal pressure needed for that cavern. If we go for 15 megapascal, then we will have 90% of sigma V, and it's going to be safe. Everything will be safe. If you would like to have 26 megapascal, well, or 24 megapascal, then two things will happen definitely. The creep rate will increase, and of course, by that cost, we can capture more CO2. So it's like which scenario you would like to have. I found this paper by Dr. Bachou and Professor Dusseault, written in 2005. Well, there are few creep rate equations. This is what they used. And for volume change rate, normalized, and for pressure drop, normalized change, they basically offer these two equations, which basically measure the volume change during time and pressure drop during time. Okay, that's for CO2. Let's move on to hydrogen storage. Well, having hydrogen is very similar to gas storage. You have almost exactly the same thing. You have a cavern, you will have some surface facility, and you inject hydrogen into that cave. The very interesting things about hydrogen is basically you can have very high amount of electricity very fast. And if you can see in this picture, it's unmatched because you may have compressed air which you pump a day and the other day you can get it and you can produce electricity. But for hydrogen, the thing is you may have high volume of electricity very fast if you have a storage of hydrogen. And I come back to this diagram later. So this is one benefit of having hydrogen. This is a very typical schematic of hydrogen storage. You have a renewable energy, which is basically wind or sun. You started sending that to the grid. If you have anything more, like the demand for that electricity is going up or down, if you have some extra, you can bring it back to a cell for electrolysis of water. You can get pure hydrogen. After that, you will inject that hydrogen to the ground or to the cavern, to the salt formation. Whenever you need it, whenever there's a very fast need, you can get it back. And having a gas combustion unit, you will start producing electricity and put it back to grid. So it's very simple. The point for hydrogen is we can get very fast electricity. I basically found three main sites for hydrogen storage. One of them, the biggest one, is in United States, Texas. The other one is UK. And this is what I looked into it. This is basically located in Turkey, close to Ankara and close to Istanbul. And I think this is why they wanted to have that unit over there, because it's close to two big cities. There's a Salt Lake Site formation like every other salt cavern. The problem with brine management is there, but this is the place they wanted to have hydrogen storage. As I mentioned, I found three big sites for hydrogen. The biggest one is in Texas. The storage volume is really huge. Just think about it, 600,000 cubic meter. It's like huge, huge. And as we talk, the energy, it's really high. Another one is in UK, which is smaller, but they have 3 caverns. Each of them is 150 cubic meter. And they start using it whenever it's necessary. For Tozgolu site, because they wanted to design a cavern, these are the lab data for that Tozgolu site, and I show you the map. And given these data, they started putting everything to these equations. and I don't want to really talk about equation. I will go very fast to the conclusion, but it's very simple. It's basically having a strain rate or closure rate or creep rate related to sigma n. What I really want to emphasize here is that A, which is called creep material model, N, creep strain rate factor, and Q, which is an activation energy, is determined in the lab. So these three things is determined in the lab. And I really want you to think about it. What we usually do testing creep rate in the lab, we have a salt formation, we have sigma 1, okay, we want to be more exact. Sigma 2, sigma 3, okay, we want to be even more exact. Then we introduce temperature, and basically we determine these three things, Q, A, and N. And this is something I really wanted to focus on this in this presentation. For Tozgolosite, they did a stability design. They thought they may have three shapes when we have an internal pressure of 8 megapascal. And as you can see here, and of course we could guess that this oval shape is more stable, whereas this cylindrical shape is less stable because of these edges, sharp edges. Assuming that we can make exactly this shape, of course we do not have that much control. Of course we have some control, but assuming that we can make exactly this shape. But all of them are safe. If you would like to have either of them with 8 megapascal, all of them is safe. None of them is going to be in dilation region, and nothing will happen when no failure will happen. Okay, as I said, I was working in lab as a geomechanical engineer for a few years. I started thinking, assume theoretically we have a cavern and we would like to fill it with different gas. Now let's put aside supercritical CO2 or any gases. Assume that we have two ideal gases, and we would like to basically fill that gap, that cave, with two different gases. The question is whether the geomechanical parameters, and I'm specifically thinking about a strain rate, volume change drop, and pressure drop. The question is whether these parameters may change if we go from one gas to another. Because as I mentioned, usually what we do in labs nowadays, what we have is very simple. We have a rock, which is a salt rock. There is no interaction, and I mean no interaction between the gas, internal gas, and that salt. And let's put aside, there will be no chemical reaction between that gas. So I'm just focusing on physical effects. So let's move on. Let's see whether they are different or not. Well, you probably should know that I put something like this for all equations. I put CO2, H2, doesn't matter. Think about two different gases, right? And I assume this is one formation. I assume the temperature gradient is basically the same in both cases. Okay, let's see, Q is the same. We are talking about ideal gas. Let's think R is the same. I read some literature, and almost all of them suggested A and N is only a function of salt formation, and that's it. And basically in that salt formation, A and N, it's dependent on fabric and moisture. So I thought, okay, we are talking about one formation, so they should be the same, right? Said, okay, let's for now, let's assume that these are the same. So let's move on, see what's going to happen. So cool. Having those assumptions I made, whether they're right or not, and we'll talk about it. I figured out that its strain rate, the closure rate, is independent of any internal gases. It means that you have a cave, you put it with nitrogen, hydrogen, whatever. It's totally independent. The volume change rate is, again, independent of internal gas. So you shouldn't be even worried about that. What I figured out was about pressure drop. It was very interesting that I figured out, hey, you know what? It is a function of compressibility of gases. And then I started, maybe I made some wrong assumption. And I came to the class and talking to Professor Dusseault and my other graduate students, hey, you know what? I came to this conclusion. I'm not pretty sure whether I can assume A and N is constant. Because at the end of the day, pressure drop is a function of compressibility. And of course, I know that we can measure compressibility in lab tests with other apparatus, but intuitively, we may think about it like this. If pressure drop is a function of compressibility, why we cannot introduce gas while we measuring creep rate in labs? So I thought, okay, that's a good idea. And we talk in the class, and Professor Dusseault was like, okay, that's good things, because that raised a question whether we can assume this is true or not, because I couldn't find any paper and address that. So these are the conclusion I made, basically. Assuming what was assumed in my research, as I mentioned, creep rate is independent of internal gas. Volume loss rate, independent. Pressure drop is dependent on compressibility. And what I really, really, really want to emphasize, and I have like, okay, 2 takeaway messages for you. Let's have more lab data. And it's not because I was working in lab, because we may not be able to assume that A and N is only dependent on salt formation, because it may be different. We haven't done many tests having internal gas in contraction with salt. I make you an example. Assume that we have a salt formation or salt sample, and there's a very small mini fracture in it. If we have hydrogen, which the molecule size is very small, and if we have air, which the molecule size is very big. So intuitively, hydrogen can penetrate in that fracture, while molecule of air may not. And these may change fabric, may push moisture. So if you ask me, hey, can you tell me they are important, or if we start testing these with different gases, does it matter? I really have no doubt. I really have no answer. But the question is, we really need to examine that. We really need more data. So first takeaway message for me is, if you have a cave, you wanted to fill it with compressed air, which is okay, definitely. If you wanted to reuse it for some other purposes, think about it. We may need to redo all geomechanical tests again. The second things I thought about it, I found this in Tozgolosite. Tozgolosite initially designed for compressed air. But it was interesting because they have caverns for compressed air, and within that formation, they had some caverns for hydrogen. Why? It was very simple, because of that graph I showed you. Hydrogen can produce lots of energy very fast. So I'm suggesting, if you're using compressed air in Ontario, well, we have, thank God, we have water. We may think of having some hydrogen storage as well. It's not something that, okay, this is the bad thing, let's do it, but let's think about it. Okay, we we are going to design everything for compressed air, it's worth thinking about storing hydrogen too. And in the last year WISE, I guess seminar or whatever, we had some gentlemen talking about having hydrogen in Toronto. So that could be an option if you would like to think of storing high volume of hydrogen. And that's my second takeaway message, basically. Thank you very much. I appreciate your time. Thank you, Professor. So I'm ready for any question.
I have no questions that have come through my computer from the people who are listening remotely. Are there any questions here? Dr. Jackson?
Mohammad, that's very interesting. Can you talk a little bit about the properties of salt? Like what you would expect the entry pressure to be, what you would expect the porosity to be, and the state of saturation. Fully saturated?
Sorry, can you start again? It's on.
Yeah. Could you speak a little to the issue of the petrophysical properties of the salts that you're dealing with, Lotsburg and the Turkish example? Entry, critical entry pressures, state of saturation, porosity, and so on and so forth.
Thank you very much, Dr. Jackson. That's a good question. Salt are considered impermeable. It means that K is very low, porosity is very low. If we are thinking about bulk volume of salt, the porosity will be very, very low, the permeability very, very low, but we may have some kind of very small fracture on the surface, especially when we have brittle salt, right? Because we have more brittle, and sometimes we have more brittle, sometimes we have more plastic side. Another thing that really matters is the temperature or activation energy. The higher temperature it is, the more plastic behavior of salt will be. So you may think about it like in which depth we are talking about salt, because if we are going deep and deep, the temperature is going up and up, and then we will think about higher creep rate. Because it's more like a viscoplastic things, when we go to the salt formation, sigma 1, sigma 2, and sigma 3 are all the same. Because it's more like a, maybe I can say gel or something. So it's more like a very viscous material. So I'm not pretty sure. Did I answer your question, or is there anything I can help?
Let me amplify just a little bit, Mohammad. The porosity of salt varies from about 0.5% to maybe 2.5%. The bedded salts tend to be wetter and have a higher porosity. But even with the higher porosity, the channels between the grains are so narrow that the capillary entry pressure for a gas to displace the brine that is in between the crystals is extremely high. So that salt is viewed as being impermeable to a phase that is not aqueous, to a non-aqueous phase. To an aqueous phase, it's considered to have permeabilities on the order of 10 to the minus 18 to 10 to the minus 20 centimeters squared per second. So that's much, much lower even than a very, than a very clay material, very clay shale. The issue is more of the roof rocks. Are they impermeable? And those are research questions for us.
What about the presence of, in the bedded salt of the WIP site, the waste isolation pilot plant in New Mexico, which is used for storing nuclear waste, there the quote aquifer, unquote aquifer, was anhydrite beds within the salt. So how, and they were much more permeable than the salt itself. So how frequent are those within bedded salts at Lotsburg, for example?
Yes, I studied the Lotsburg. Mohammad, if you don't mind, is that?
Oh,
I studied the Lotsburg quite a bit in the context of of some years ago, storage of materials. The Lotsberg is a recrystallized salt, so that it is extremely low permeability, and there is one streak in the middle that is not even present anywhere, pardon me, everywhere. It's an ideal location for very, very secure storage. We don't have to meet the same standards for compressed air energy storage as we do for hydrogen, or for, say, a material that is toxic or radioactive. There, much more relaxed because air does not have any environmental impact. But Lotsberg is beautiful. Our bedded salts here in Ontario, they're thinner, somewhat less desirable, but the next speaker will address some of these geological issues. Jay?
Thank you very much.
Could, come.